You were asking about, for a bit of clarification about what polarization means. Well, polarization can be applied to one or two different things. It can be applied to light, it can be applied to batteries, in effect, electrical components, magnets. So the batteries in your remote control, they're polarized in effect, aren't they? Because you've got a positive side and a negative side. And if you put them in the wrong way round, they won't work. In other words, well, the device that you're putting them in is polarized, really, isn't it? Your remote control won't work if you put the batteries in the wrong way round. So you could say it's polarized, in a sense. But if you were just using that to light up a little light bulb, it wouldn't make any difference. It would, if you connected that up to a light bulb, one side's positive, one's negative, it would light up the bulb whichever way round. It wouldn't make any difference, would it? So you'd say that would be unpolarized. The light bulb would be unpolarized. The battery's polarized, but the light bulb wouldn't be, because the light bulb doesn't care about polarity, because it's just a resistance, isn't it? It doesn't really care which way the current's going. Okay, now that's a simple example of polarization. Let me think of others then. Loudspeakers. I'm going to wonder where I put that battery in a minute when I need it. Loudspeakers. There's one here. This is a big loudspeaker. Like it. This is a sort of that your dad would have loved, or your brother. I collect these things. I don't know why, because I've been obsessed with them since I was 11. So I used to collect them then, but little ones. And yeah, I used to collect things like this. And if I got a 4-inch, if I got a 6-inch speaker, that would have been big. And when I was 11, 12. But now, this is kind of the norm. This is a really good top-notch mate, but like the sort of the wood user. When you go to a big gig, big concert, the sort of speakers they have inside would be made by people like this. Precision Devices, a big speaker manufacturer, obviously of professional speakers. But this is a relatively old one now. But that there in the middle is the cone is free to move in and out. You can see, can't you? It can move forward, and it can also thrust forward. Sorry, it's too heavy. Got exercise, isn't it? But anyway, I managed to crash the camera. Well, crash. It just stopped working. I think the wire must be getting a little bit broken inside. Anyway, back to polarization. the point I was trying to make about Gary's design of a loudspeaker wouldn't be polarized. Let me show you how a normal loudspeaker works. The cone I showed you in that. Hang on. So, in a normal loudspeaker, a real loudspeaker, the cone, it can move. It can be pulled in, yes, and it can also be pushed out by the coil of wire, the voice coil as it's called, that sits in a very thin, a very tiny magnetic gap. That is a powerful magnet. That's one pole of the magnet. And that's the other pole of the magnet. Sorry, tell the right. Okay. So the way the magnet's constructed, it is a little bit complicated to describe by me just pointing my finger at it. You need to see a little cross-sectional diagram. But essentially, the coil is sitting in the north pole that side and the south pole that side, so it's a very strong magnetic field between the two in that gap. The smaller the make your gap, the more powerful, the smaller you make the gap, the more concentrated the magnetism becomes across that gap. So the voice coil, which I'll show you now in this other one, so that's the voice coil. a coil of very fine wire that the audio signal is fed into through these little flexible wires. I've gone somewhere. Little flexible wires. It's fed into the voice coil. The audio signal, which is an alternating current signal. Got hair in my mouth. It's an alternating current signal. So in other words, it's polarized, a bit like that battery. I'll get that battery again. It's a bit like that battery. The current that's fed into that coil, so it keeps changing polarity. So it's polarized that way, then that way, then that way, then that way. It's alternating. It goes up and down. It's AC, as they say, alternating current. A bit like the electricity that's supplied to your house. That's alternating current, but that's a regular, 60 cycles per second in America. I think it's 50 cycles per second in Britain. I hope I remembered that right. As you get older, your memory fails a little bit. Right, that's a pictorial idea of what an alternating current looks like. The picture's a bit fuzzy. I'm not sure. Is my camera dying? Anyway, yeah. So that's a visual idea of what an AC waveform looks like. That's what they call a sine wave. It's a nice smooth up and down, and it basically means that that's when the current is going one direction. That's when the current's going one direction, reaches a peak, then reverses. Well, it doesn't reverse yet as such. It collapses back down to zero, then it reverses direction and goes the other way. Builds up negatively. That's like turning the battery the other way around. Builds up negatively, reaches its peak, goes as far as it can, then starts to collapse back down again until it reaches zero again. So zero, maximum positive, collapses back down to zero again, crosses the zero line, goes as negative as it can go, and back to zero. And that repeats in the case of electricity supply to your house in America. I think it's 60 cycles per second. So it'll do that. Positive, negative, positive, negative, positive, negative, 60 times a second. Hertz. See, I don't know how much you know. I don't want to be telling you things that you already know, but there's no harm in going over things again, is there? Sometimes I can add a little bit, maybe add a little bit to what you already know, flesh things out. Any questions you got, I'm happy to answer, by the way, but I can't promise that I won't digress and start talking about cat litter or something that's nothing to do with. I learned the other day that cat litter, it causes some sort of problem at airports. Who's taking cat litter to airports? Anyway, but apparently is it radioactive or something, and it causes some sort of reaction. I think bananas too. But anyway, but cat litter and bananas can cause problems with the radiation detectors at airports, apparently. I don't know much about that kind of thing. I just heard that. Anyway, moving swiftly on. So I'll pause a minute. Oh yeah, so anyway, when you feed AC into a loudspeaker, a real loudspeaker, not Gary's fantasy version of a loudspeaker, the current that goes through that voice coil, there, you can see attached to it, not a steel rod. Attention folks, not a steel rod. This is not a steel rod. I keep thinking the camera's there because it was yesterday. I'm looking at the wrong place. The current that goes through that is constantly changing direction. It's changing polarity. So 1 minute it was... Where have I put the battery? Yeah. So 1 minute it's pointing that direction, then it's that direction, then it's that direction again. And it's alternating because the vibrations in the air that are converted to electrical impulses that are amplified and then fed into a loudspeaker, those are alternating. In the case of music and our voices and sound in general, it's not it's not a straightforward simple waveform like this. It's a lot more jiggly, isn't it, and up, and because it contains a very wide variety of frequencies, 20,000 cycles per second, 10 cycles per second, subsonic. We can't hear 10 cycles. and at my age I can't hear 20,000 cycles per second. Your age you probably can. Females and young people can hear higher frequencies. But anyway, it's by the by. So anyway, if you feed an AC, an alternating current waveform, electricity that's alternating into a loudspeaker, if you connect it one polarity, it'll push the cone forward. Say that. But if you connect it that polarity, it'll pull the cone backwards. That's how a loudspeaker is designed. It's designed to push forward and pull back. Push, back. Yeah, push, pull, push, pull, push, pull. It's a piston-like action, because when you fix that speaker in a box, an enclosure, a baffle, that goes under a lot of different names. You know, the big box you see on stage, typically. That stops the compressions from the rear of the speaker reaching the front of the speaker, because that cancels out. You know, they cancel one another out, because while the front of the speaker is compressing the air, it's decompressing the air behind. So yeah, so the front of the speaker is going forward, that's compressing the air, but behind it, it's decompressing the air. So that's why a speaker has to go in a box, really, an enclosure, so that you only receive the compressed side, so to speak. You don't want, well, it's a bit more complicated than that, but in general, the speaker manufacturer is trying to stop the sound from the back of the speaker reaching the front, because they are out of phase. One's going that way, the other's going that way. That's polarization, in a sense. One's going that way, it's going the front of the speaker is going forward, the back of the speaker is the front of the speaker is creating compressions in one moment. At the same time, it's doing a decompression behind it, so the sound cancels out. That's why if I connect this speaker up and feed it with, you know, some ridiculous power, it won't sound as loud when it's out of the box as when I put it in a box, because when it's in a box, the two sides of the wave are not cancelling one another out. These things are best learnt really by actual doing. Learning from books is one thing, but actually connecting things up and doing them is another, and then you learn a lot more. But it's a lot more long-winded. You end up being an old bloke like me by the time you know these things. See, I don't know these things until you have to waste, you know, days, weeks, months, years trying different things and working out, and then you piece it together. Now, this is what Gary claims he's done, but you know, for a 70-year-old bloke or whatever he is, he can't possibly have done what he claims to have done. Because if he'd spent his life taking things apart and putting them back together again, I don't think he's even done the taking apart bits at stage. He would know that a loudspeaker cone pulls in and pushes out. So it compresses the air and it decompresses the air. So the front is compressing the air while the rear is decompressing, and vice versa. But so the speaker cone is supposed to be polarized. It can push and pull in equal measure. Now, according to Gary, it only pulls. His theory is it only pulls. It only does this. It pulls in, and he says it doesn't matter what speed that happens, because the next bit is the important bit. According to Gary's stupid theory, he says, ping, it goes ping forward faster than the speed of sound. Remember that, faster than the speed of sound. All due to the elasticity of the cone. Ping. Did that look faster than the speed of sound to you? Ping. And it creates a mini sonic boom. Right, so he would argue that what I just showed you there was invalid. He'd say, well, I can't release my fingers faster than the speed of sound, so, but, you see, he's got a million excuses, anything to defend his daft ideas. So, but anyway, he says that electrically, the steel rod that isn't there, is pulled into the solenoid, the fixed solenoid that he calls an actuator. It's not called an actuator, it's called, well, that's a magnet. That's called a voice coil. That's called a spider, that bit there. You don't need to know really, but spider. That just helps keep it so it's a piston-like action, so it doesn't go sideways or twist or anything. It's to try and control the cone so it only moves in that plane. Yes, doesn't wobble or anything like that. I forgot what I was saying now. Hang on. Now magnets are polarized too, aren't they? They're dipoles, I suppose. Yeah, magnets are polarized too, aren't they? So you have a north and a south, and they have poles. North pole, south pole, polarized. Okay, that's pretty obvious, isn't it? Yeah, that's pretty obvious that that's different to that. This isn't actually a magnet, it's just a mock-up of one. Not that it matters. I don't actually have a magnet of this sort that's easy to show. So, magnets are polarized. Now, in connection to the polarization of magnets, when electricity is generated, you see that obviously? Little hand-wound generator, dynamo, call it what you will. That's just a miniature version of how electricity is usually generated to power our homes. You know, forgetting, you know, rooftop, what do you call it, solar panels and all that. But generally speaking, electricity is generated by turning essentially magnets in the vicinity of conductors, typically copper and aluminium. Well, usually copper. Copper's a better conductor than aluminium. Aluminium, good conductor, but and lighter weight. But copper is better than aluminium. Only a bit, but anyway. So the point is, we're in that little dynamo I showed you there, that little generator. What's in effect happening is, it's a rotational way of doing this. Like a north pole sweeping past some copper wire, and then so that's the north pole, isn't it? North pole, then a south pole, then a north pole, then a south pole. It's constantly, it's like sweep, because it's going in a circular motion. If you can picture this sweeping, going around and rotating in the circular motion, it would be alternately inducing current from the south end and the north end, the south and north. So that would be inducing positive then negative, then positive then negative, then positive then negative current in the copper bar. That's how electromagnetic induction works. I don't know if you already know this, you see. I don't really want to be, you know, insulting your knowledge. If you already know it, you know what I'm saying. I'm just covering everything as best I can. Just filling in the gaps that any gaps you might have, because you seem quite genuinely interested, and that's fantastic. I love it. You'd made a great electrician, you would, because you actually are curious enough to want to know these things. So the way electromagnetic induction works, which is what Faraday essentially discovered in the early 1800s, it's essentially when a magnet is moving past or in the vicinity of, I'm putting it in cruder terms, a professor like Walter Lewin will explain it in much more complex terms, will make it sound a lot more complicated than it is. They'll talk about loops, and writing all the Greek, Latin symbols, God knows what, on the blackboard, and equations. They'll make it sound a heck of a lot more complicated than it needs to be. Now, there'll be people all over the internet arguing that mathematics is absolutely crucial to understanding physics. I would argue that it's not quite as important as they think it is. And my evidence for that is the fact that I was the only one, I'm not bragging now, but I'm just trying to explain, otherwise I can't explain. I was the only one out of about 80 students when I was an apprentice electrician. For the entire 4 years I was studying, it takes that long to qualify really properly. I was the only one who ever got regularly 98%, 100%, 96%, in my exams, and all the people around me who were good at maths. I'm not very good at maths. Quite hopeless, really, because I missed out on a year's worth of education when I was a kid, by the by. So I never caught up on maths, but I was surrounded by people who were fantastic. They could do quadratic equations. I still don't even know what they are, and I don't want to know. If I'm honest, it'll do me head in. It's too much for me. It just doesn't help for me. But despite the fact that they were all fantastic, really good at mathematics, which is brilliant for them. I had no problem with that, and I wasn't. They didn't like me, apart from the fact I was very shy and unsociable because I have Asperger's syndrome. So I didn't go out to the pub and socialise with them and all that. So they thought I was a bit snooty. It wasn't that. I was just very shy and unconfident. I lacked confidence. So, but they thought I was standoffish, and I just didn't want to socialise with them, which was true up to a point. But, where was it? I've lost track. Oh yeah, so they were upset at the fact that I always passed the exams, with top marks, no difficulty whatsoever, because I understood electricity, but I was no good at the maths. Now they were the opposite way around. All the other students at college, they'd be lucky if they got like 80%, 86, I think in one case. I remember this guy, he was dancing around the room. I thought, well, if I got 86%, I'd be a bit worried. That there's 14% of my knowledge that was wrong. That didn't seem to bother them. But most of them were getting about 70%, I think. But they still passed. 70 was a pass. I've no idea how you become an electrician when a third of what you know is wrong. It doesn't make sense, does it? But anyway, such is life. Yeah, but so they were great at maths. I was hopeless at it. And to the point where the lecturer told everybody when I wasn't there that he thought I was cheating the exams. I was off sick, and the only friend I had there, John, he told me, he says, Mr. So-and-so, he told everybody he thinks you're cheating on the exams because you keep getting 98, 100%, 96%. I wasn't cheating, I just understood the subject. He thought I was cheating because he used to set homework questions every week, and his homework questions were really maths tests. Even though we were all studying electricity, he managed to bias the questions in such a way as you could only talk about equations, and I'm lost. So he was setting me up for failure. I don't mean personally. I'm saying that because most people are great at maths when you go into college and doing anything about physics or electrics, whatever. A lot of professors and lecturers and students, they prefer mathematical questions because for them, understanding things from a mathematical point of view is, I don't want to say easy, I don't know, I'm not in a position to say, but for them, yeah, it comes more naturally for them to answer questions in mathematical terms and write a load of squiggles and equations and, great, tick, 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 So they would get like 80 odd, 90%, whatever, in their homework questions over the course of an entire year. And at the end of the year, they'd work out their average, and they would all get like 80, 90%, whatever, because they're great at maths. And the questions that the lecturer had set for us were essentially maths questions, as far as I was concerned. So I scored low. I'd get back 30%, 35% if I was lucky. And so they looked down at me and thought, "Oh God, how did he get on this course? He's clueless." Me. They thought I was hopeless. But come to the actual exam, 98% every year, every single time. It sounds like I'm bragging, but I'm just trying to explain the point that when I explain something to you or anyone else in quite simplistic terms, you're learning from somebody who understands it sufficiently enough to pass exams with virtually 100%. Whereas somebody with a mathematical bias, like Professor Walter Lewin, and most people really, they will explain, when you put a current through a loop of copper wire and cross-sectional area this, d phi, dt, my brain just fries then. If I really slow it down, I can follow it, but they present the information back to me in a fashion that I think, well, I don't understand electricity after all these years of thinking I understand electricity, but listen to Professor Walter Lewin, I don't think I do anymore. But I do understand electricity. I know that when you sweep a magnet past a conductor, that's going to induce current to flow in one direction in that conductor. Well, if it's in a circuit, if it's not in a circuit, connected to a light bulb or something, no current can flow. It's got to be in a circuit for the current to flow around it. But anyway, so when you move a magnet near a conductor, it induces current in that conductor, so long as the magnet is moving. As soon as you stop moving the magnet, the current stops moving. the current is the electricity itself, so to speak, that's moving. It's a physical thing, the electrons moving. Apparently they move really slowly, but it's by the by. It generates a voltage. The voltage, the EMF as they often call it, it's supposed to be technically different, but I'm a bit, I'm not so sure. It stands for electromotive force. Electromotive force is the force that pushes the current around the conductor. Am I giving you too much information? I apologise if I am, but I'm sure I am, because even I'm thinking this is too much, probably. But anyway, so the magnet moves near the conductor, moves the current around the conductor in a particular direction. Now, if I was to change the polarity, because this is what we're on about, isn't it? Polarity, polarization. If I was to do it at that end of the magnet, and I push, and I move the magnet, past the conductor, the current would be going the opposite way. So if this is a spinning magnet, like in that little dynamo, little generator example, because that's effectively a spinning magnet, or spinning conductor, it makes no difference, so long as there's movement relative to one another. In other words, as long as the field lines, so to speak, from the magnet are effectively cutting through the conductor at 90 degrees. That's how it works. And this is what Faraday discovered. Michael Faraday in the 1800s. When it's that polarity, the current goes one direction. When it's that polarity, the current goes the opposite direction. So a spinning magnet a spinning magnetic field, a changing magnetic field will induce a changing direction of current through the conductor, and that creates an alternating current. And if you feed that current into a loudspeaker, it will thrust the cone forward and pull it back. Thrust it forward, pull it back. But it's not springing forward like Gary thinks. It's being physically pushed forward by the electricity that's fed into that coil, which changes electricity into magnetism. So then you have, it'll change from south to north, south, north, south, north, which will then be repelled or attracted to the magnetic field it sits in, that very thin magnetic field. Do I have an example I can show you of that? Oh, no. Can't show you everything at once, can I? So anyway, that's okay. Let's carry on with induction, because it is important, and I think if not now, sometime in the future you might want to know. So this is it. This is electromagnetic induction. Magnet, electro, electromagnetic. So the magnet moving near the conductor induces current in it and moves it, forces it one direction. Different polarity sends the current the opposite direction, and this has to ideally happen at 90 degrees to one another. If to that direction, it doesn't induce much current at all, because apart from the stray field lines that cut through it, because the field lines that go around the field lines around a magnet, some of them would cut through the conductor. So even if it's orientated wrong, it would still induce some, but not much. It would induce maximum current in that direction, 90 degrees to it, perpendicular. Right. So now the interesting thing is, see, it gets more complicated, I'm afraid. Simple but complicated, not as complicated as Waterlooing would make it. When the magnet is moving toward the conductor, it's inducing current one direction, and it's moving away from it. It's still inducing that same current in that direction, but it's descending. It's on the descendancy then. It's on the descendancy. See, when it was moving towards the conductor, it was rising to a peak until it got to the conductor itself. Then as it passes the conductor and it moves away, it's inducing less and less and less, because the magnetic field is weaker as the further away it gets past the conductor it's inducing in. I feel like I'm doing a not too great job now. All of a sudden I'm making it sound too convoluted. But let me pause a minute. The next. So it's moving. So it's moving past the conductor. So it's inducing an increasing current, reaches a maximum, then starts to fall down again. But if it was to come the other way, it would induce the current the other way. Now that might not be too intuitive. Let me think about that. Okay, I've tried to set up a little demonstration here. I don't know if I can get the camera to... It's quite a short lead, to the USB lead to the computer, so I don't know if I can get it. Basically what we've got here is like a north and a south magnet attached to this old rusty device, so that we've got a strong magnetic field in that gap, which is quite similar to the gap that the coil of a loudspeaker would sit in. The closer together you can get those poles of the magnets, the tighter the magnetic field becomes, so the stronger it becomes, the more concentrated it becomes in there. So, but I've got it set quite wide apart there, so that I've got this coil of wire. Instead of before, I was showing you, I was trying to explain how, you know, an actual piece of copper bar or copper wire, a magnet sweeping past that induces current in one direction or the other. This is with an actual coil of copper wire, so that magnifies how many so it's like it's cutting through 100 or whatever, 200 pieces of copper at the same time, so it's increasing voltage. The current's the same, but the voltage is increased. Anyway, sorry, too much information. Right, anyway, so that coil of wire, I've wired it up. I've wired that coil of wire up to, through those wires you can see, to this meter here. So then I can show you, if I can hold everything in the right place at the same time so the camera can pick it up. So I can show you that coil of wire passing through that magnetic gap, yeah, in the magnets in the device, inducing current in one direction when it moves one way and the opposite direction when it moves the other way. That's the point. I don't know whether I might struggle to... What was I doing? Oh, I forgot, because these are made of steel. These are made of metal, steel. They're sticking to the magnets. Forgot that. Okay. Now, can I... Well, I don't know how I'm going to physically do this. It's tricky, isn't it? I can't really put it upside down, can I? Hang on. Pause. I've got an idea. Okay. So I don't know if this will work, but I've stood the meter on top of a Mr. Kipling exceedingly good Battenberg cake, which I love. It's just the right height for what I needed though. So, how can I do this? I'm right-handed and I'm trying to do it left-handed. So, hang on. I can edit this after, can't I? I think. So you see the needle go down, it goes up when you move it one direction, the opposite way. Yeah. See, the snag with this meter is, I really need one of those meters that can go where the needle's in the meter. Ideally I could do with one of those meters where the needle is in the middle, starts in the middle and goes left for one polarity and right for the other polarity. This one only goes one polarity. It's polarized. So the needle, when you send electricity through it in one direction, the needle will go to the right, but it can't go to the left. So when you feed the electricity in the other way, it can't physically go to the left. Only a tiny bit, and it's bad for the meter because I could damage it. So the coil of wire, my hands are in the way. So the coil of wire, when it moves in one direction, so it's going down, but when I move it the other way, it goes up. So it's going down, up, down, up, down, up, down, up. Negative, positive, negative, positive, negative, positive, so to speak. So that's just to try and show you electromagnetic induction. Hope that was reasonably clear. Wonder if I can move it a bit closer so that you can see it a bit better. Right, I've moved the chair closer so you can see a bit better. So magnetic field between these two magnets, north, south, I think, whatever. I think. I talk rubbish sometimes, not too often, but meter. Right, so let me get that coil of wire again there. So when I move the coil of wire, I'm waiting to see both there. So when I'm moving the coil of wire into the magnetic field, it goes one direction. Then when I stop it, it just stops altogether, doesn't it? Then when I pull it out, it induces it the other direction. Thrust it in, goes one way. Pull it out, it goes the other way. But notice that when I'm not moving it at all, I'm just holding it there, steady as I can, with my shaky hands, it's not generating any electricity at all. But a microphone essentially works on this principle that the vibrations, I mean most dynamic microphones, moving coil microphones as they're called, the most common microphones that most people use. There are different types, but most common microphones, they work on the principle of exactly the same as a loudspeaker, but in reverse. So the vibrations in the air attached, the vibrations in the air vibrate a diaphragm, which are attached to a coil. Here we have a coil, don't we? A coil. And that vibration makes the coil wobble in and out of a magnetic field, like this. And that makes the vibrations that represent the sound that it's picking up. Those are then amplified electronically, either by valves, vacuum tubes as you call them in America, in the old days, and these days transistors. That's amplified to a magnitude, a strength of electricity that's then powerful enough, because this is very weak electricity, obviously, it's then amplified to be strong enough to generate the equivalent currents, to generate the equivalent of these alternating currents, these waves as they look like when you view these on an oscilloscope on a screen. These pictorially, these visually look like waves on an ocean, but it's only a visual representation. It's not waves in the literal sense of the word. You see, waves can mean so many things. This is where a lot of confusion arises when people talk about waves of light and waves of electricity and waves of water and waves of sound. There are very many variations of waves. There's the Queen's wave, Queen Elizabeth II, the royal wave, the royal wave. Right, I'm talking shit now, aren't I? Sorry, mate. Right, okay, let me just stop a sec. Right, so those uppy downy signals from the meter reading there, induced by that coil moving in that magnetic field, that when you represent that on an oscilloscope, that device that lets you see electricity in a visual form, that you can measure the amplitude, the strength of the signal, and the speed of it, etc. An oscilloscope. It looks like a wave. It looks like that. I don't get these the right way around. It looks like a very uppy downy signal. So you can see then the rise and the fall, and so it's going positive, then back down to zero, then negative, till it reaches a peak, and then back down to zero. So that's called a crest, and that's called a trough. Crest and a trough. And those are the peaks. That's the peak of the crest, and that's the peak of the trough. I get mixed up sometimes. I end up calling that a peak and that a trough, but technically that's a peak and that's a peak. Yeah, and that is the wavelength, if you don't already know. The wavelength is between that point and that point. Or, yeah, that's the time it takes. This is the timeline. That's the time it takes for the current to go that direction, fall back to zero, go back the other direction, come back to zero again. That's the time it takes. So the wavelength of light is extremely fast. It's doing that extremely fast in electromagnetic terms, that is. We're getting into a bit of a, I don't want to say grey area, but a difficult topical area, because there are different ways of thinking about what light actually is, but don't want to go down that road just yet. It's a bit too much. But your question was about polarization, and I'm trying to address that. So, yeah, okay, so anyway, light is electromagnetic. For now, just assume that light really is electromagnetic, exactly as Maxwell proclaimed. Maxwell, the mathematical guy, the mathematician, who worked with Faraday in order to put Faraday's discoveries in mathematical terms, I suppose. That'd be a crude way of putting it. Now, hang on a sec. Yeah, so anyway, it turns out that light and radio signals, they're all the same stuff. They're all electromagnetic waves. Theoretically. Richard Feynman disagrees. He says they're not waves, it's particles. Einstein's work kind of confirmed that it's essentially particles, but or as a particle-like nature. This is where the double slit experiment comes into being, really, to some extent. It comes into play anyway. That aspect, it's not straightforward. That's all I'm saying, mate. I don't want to delude you into thinking it's really. I don't want to sort of say it's really this or it's really that. I'd like to try and present you the information from a mainstream point of view, not Gary's "they're all wrong, they're all idiots" point of view. That's silly. I have my own ideas, my own hypotheses, but I could be wrong. So there's nothing wrong with having a hypothesis that goes against the mainstream, so long as you're not trying to sell it to kids, especially like young people. Older people, they've lived their life, but younger people, you don't want them to be starting off on the wrong foot and listening to Gary teaching them absolute rubbish about physics, especially electrical physics, things that are really easy to prove wrong. But because he talks so much nonsense, he fires there's so much nonsense even in one hour episode, and he does one every day. It's just impossible to, well, not impossible, it's just very, very time consuming and difficult to untangle. And a lot of people get swept along with that. As luck would have it, most people who get swept along with it probably have no potential for real science anyway. Because if they're so gullible as this, that think that Gary is talking sense, for any length of time anyway, if people who follow him for years and never realise he's talking utter rubbish, well, they probably weren't cut out for science anyway, really, in truth. Right, where was I? I lose track, you see. Sorry, but you don't seem to mind. See, that's great. I'm really glad that you don't mind. Although I try to limit it because I can take the piss sometimes. I just bore the shit out of people. Anyway, so that's a waveform, but electrically it's not really a wave, is it? It only looks like a wave when you put that electricity through an oscilloscope, so you get a visual image of it, and it looks like a wave. But electricity going back and forth, changing direction, alternating polarity, that isn't literally a wave, is it? Not when it's electricity. It's just electricity going. It's like water going to a pipe. If water was going to a pipe and it's going one direction, and you push it, then you pull it, then you push it, then you pull it. Imagine you've got water in a sealed pipe. A length of pipe, sealed both ends with water in it, and you press one end if it's like a membrane at the end. This is a bit like how a capacitor works, incidentally, but another different topic. You press one end, you'd see the other end bulge out. I made this. The balloon material burst after a few weeks and water went everywhere. So, but if you press one end, the other end bulges out because the water's travelled in it as far as it can go. Then when you let go, it springs back again, and that's like alternating current in a wire, really. It's moving. It moves that way, then it goes as far as it can go, then it comes back the other way. So it moves that way as far as it can go, then it comes back the other way, goes the other direction. An actual model would help you. I can't be bothered building one, to be honest, because it takes quite a bit of time to do it and seal it up so the water's not leaking everywhere. I do have a limited amount of time at the moment. I should be going somewhere really shortly. This is a pleasure though, so don't feel bad. I'm just saying, like, that's why I'm in a bit of a rush and I might be sounding a little bit incoherent. Yes, so electricity going through a wire is not really a wave, but it's represented as a wave on an oscilloscope screen. It's an easy way to understand what's going on. It's a visual aid, really, but it's not really a wave. It looks like one, and so we call it a waveform, and that would be classed as a sine wave. Now, light and radio waves can be represented exactly the same, except the time aspect would be squashed together. So, in other words, this would be happening a lot more times per second. In the case of radio waves, it's typically megahertz, millions of times a second, or at least thousands of times a second. Your mains frequency that's applied to your house, like I say, it's doing that, going pos neg 60 times a second. In Britain, it's doing that 50 times a second. Don't know why we have different frequencies, but we do. And sound, your hearing range is probably up to about 16 kilohertz, roughly. I would imagine maybe 20 if you've got good hearing. So then that would be happening 20,000 times in a second of sound waves. Now, sound, you represent sound waves the same as you do electrical waves, but sound really is waves, isn't it? It really is vibrations in the air. That really is a wave in the sense that we understand waves. But electrical signals going through a wire aren't really waves until they look like them on the screen, but they aren't waves until they've been transformed into sound waves again. When that signal is fed into that coil, and it forces the cone forward, physically pushes it because of the magnetism in that coil that's generated when you feed electricity into it in one polarity, forces the cone forward, then physically pulls it back again when the current reverses direction. So the cone is being pushed forward and pulled back in a very controlled way. It's not, as Gary says, he's wrong. It's not being pulled back and then flirted forward like an elastic band, like nickel elastic. He's talking utter rubbish. I don't know how he gets away with it. I think it's because a lot of people fancy him. I think they find him attractive. That's fair enough, you know what I mean? Live and let live, you know what I mean? But it's got nothing whatsoever to do with physics. Unfortunately, neither has his channel. It's quite strange, isn't it? His channel's called Draftscience, his website is called Draftsphysics, and it's as far away from real physics as you can get. It's as far away from. I mean, if you can't describe how a loudspeaker works, if you were imagining there's a steel pole attached to that, and you think there's a lump of steel attached to that, being pulled in and out of, like he thinks that coil of wire is fixed in the basket, as it's called, the metal framework. He thinks that's a fixed solenoid, and that this is attached to the speaker. That weighs a ton. Think how much that would slow down the speaker moving forward and backwards. To reproduce sound well, it has to be as lightweight as possible. It has to have as low a mass as possible. So speaker manufacturers go to a great deal of trouble to make that strong, firm, have little to generate as little sound as it possibly can. Gary thinks the opposite. He thinks that's meant to make sound. No, speaker manufacturers go out of their way to stop that having its own sound, because that adds colour to the sound that they don't want. They don't want the sound to have the sound of the cone added to it. All the speaker manufacturers want is for that cone to reproduce the signal that's fed into that coil, which was generated by, say, the microphone or whatever, and amplified, and all through the chain of changing sound to electricity and amplifying it and back to sound again. All through that chain, they're doing their best to not spoil the signal, to make it so it's being amplified accurately. It's not being distorted. Unless it's a guitar, electric guitar, Jimi Hendrix style, fantastic. Then you want a distorted sound, a particular kind of distortion that just happens to sound fantastic, great. But in general, for high fidelity, as it used to be called, probably still is, you're trying to keep the signal as faithful to the original as possible, so that you hear really good, realistic sound. Gary's invention, Gary's imagined, Gary's fantasy version of how a loudspeaker works does the exact opposite of that. His fantasy version, where the steel rod attached to that cone would pull into the solenoid, and according to him, then releases it, boing, so it flirts forward like nickel elastic, thus generating, according to him, which is rubbish, thus generating a so-called a mini sonic boom. A mini sonic boom. Bang! That's his idea of science. Now, if he can't get that right, if he can invent that kind of crap, how can we possibly trust a word he says about how atoms work and protons and neutrons and electrons and the universe, and saying he's unified physics? He hasn't even unified hairdryers and loudspeakers. How do hairdryers make the noise they make? Do they have little elasticated things in them that keep making little mini sonic booms? He's daft. He's crackers. He's crazy, and he's vindictive and nasty and vile to boot. So the guy hasn't got that much going for him anymore. I followed him for a while because I thought, well, at least he's standing up for, he demands a better explanation for things like Huygens principle and such like that. Huygens principle, I can't pronounce the word. It's a Dutch name. So unless you're Dutch, apparently nobody can really properly pronounce it. It's supposed to be Huygens or something like that, according to Professor Walter Lewin, who is Dutch. Is it Dutch? Or I get mixed up between... Anyway, bad bye. Right, pause for thought and get onto light now. I promise this will be... The pain will be over soon. It will be over soon. Light, polarization of light and radio waves.